Now we'll see the details of individual circuits being used in AC. AC circuits are always subject to the phase and phase difference. So we'll see individually what happens when it is only R. Only R means no phase difference, because already we have discussed when there is coil, the current is bound to lag behind by 90 degree from the voltage. And in condenser, you already know that current always leads the voltage by 90 degree. It is resistance here, clear cut, you could use Ohm's law, that's V proportional to I, simply because when voltage will increase, current will increase in the case of resistance. It is the circuit for AC source is always represented by this circle having a sine wave inside, whereas for DC source you already aware. Here R equal to Vrms upon Irms. You'll have the phase for both voltage and current same. V0 sin omega t, I0 sin omega t, and resistance will be given by Vrms, Irms, both in the same direction, Vrms and Irms. For coil, we have recently in the last chapter, we have gone through. For coil, we know when current flows through it, it always lags behind because of self-induction. Soon as the current starts increasing, induced current opposes the change, and for a moment, quite in the beginning, the current becomes zero. That way, we could conclude that current is lagging behind. Voltage has been fully applied, and the current is still zero to begin with. That's why we say the current lags behind. But you see, we have followed one protocol here, that we always draw the current this way. If this is current, that means the current is lagging behind from the voltage. This is the figure for current and voltage in the coil. The phase difference is going to be 90 degree. Here you'll write the relation V0 sin omega t, and for current you are going to write sin omega t minus 90 degree. Then in place of resistance, we use reactance term. This is equal to, empirically we find that the reactance here comes out to be omega into L. You are already aware omega is angular frequency and L, you know, self-inductance. So when you want to find the current in the circuit, the formula is going to be this one. In place of, you see, resistance, you are going to have XL. You increase the frequency, XL will increase and current will decrease. That means IRMS can be increased by decreasing the frequency. You can have hyperbolic relation between the two. When phase difference is 90 degree, obviously no power should be consumed in the circuit. That's why we have wattless current flowing through coil. Now it comes to condenser, only condenser in the circuit. Before we go into detail of condenser, I would like to let you know why do we say that current always leads in condenser. You see, you compare with one very funny situation. When you are empty stomach, listen again, you are empty stomach and you are having greater amount of appetite. That time, if you are on the dining table, the rate of picking the food, that will be comparatively greater compared to the situation when you are almost saturated, then this speed will naturally decrease. This is what actually happens with the condenser. When condensers are getting charged, initially the rate of current is very high. So current is very fast quite in the beginning when the condenser is not charged. Voltage is almost zero and the current is maximum. This is the reason why we say that current leads in the condenser. Quite opposite nature. In coil, the current lags behind, and you can say in condensers, the current always leads ahead. So, for showing condenser, again, this is current. The current is leading. Other way you could say the voltage is lagging behind. Current is here leading. Here we use the term reactance, but now this is equal to 1 upon omega c, means when you will increase omega, x will decrease and current will increase. IRMS 1 upon xc, and 1 upon xc is proportional to omega. You see, the difference here is by increasing frequency, you have increase in current. By increasing frequency, you have decrease in current. You have to remember it by heart. What is inductive nature and what is capacitive nature? When frequency increase results in decrease of current, this is inductive nature. When frequency increase results in an increase in current, this is called capacitive nature. Now, after knowing all these fundamental and basic things, we could apply in compact circuits like LR and CR. Here you see LR. In LR circuit, coil and resistance both are there. Here you are going to use impedance in place of this reactance or resistance. It is going to be R square plus XL square, because you see the current in resistance is going to be same, in the same phase. But in coil, the current lags behind, or you better say the voltage leads ahead. This becomes the case of LR circuit. This is the final voltage. It's going to be phi. Current is lagging behind V0 sin omega t and I0 sin omega t minus phi. Cos phi, the power factor will be given by R upon Z. Here voltage will be given by this thing VR square, VL square. Similarly, impedance will be given by this relation. In place of resistance, you are going to have the term impedance that will again be measured in ohm only. Similarly, if we have CR circuit, it's shown over here, CR circuit. There in place of VL, you are going to write VC. It will be VC square plus VR square, likewise Z square, XC square plus R square. Here you will say cos phi R upon Z. So, in both the cases, you have to be alert. By increasing frequency, here something else happens, and by increasing frequency, the result is quite reverse to that in the case of L circuit.